Good morning everyone, and welcome to today's worked exam answer video. Today we are having a look at a question where every part is asking us about a different pair of isomers. So we're given some information about the isomers, sometimes we're given more information than others, and we have to draw one possible structure for each of the different species. So we've got A and B, C and D, E and F, G and H, and then on the other side we've got I and J. And like I say, we're given different pieces of information. Sometimes it's about chemical tests, sometimes it's about infrared spectra peaks, sometimes it's about NMR spectra peaks, sometimes it's about different isomerism that is shown. But in each case, I will highlight the key things in the question to help us, and then obviously talk through how I would approach trying to deduce a possible structure for each of the different letters. Let's get started. So as you can see, for each pair of isomers, I've highlighted the molecular formula, which is obviously very important, so we know how many atoms of each element we're drawing. I've also highlighted some key information about what distinguishes the isomers in the pair. So A decolorizes bromine water and B does not. And then I've made some annotations as to how that's going to be helpful, and I've done that for all of them, including the one on the reverse side as well. So starting with A and B, they've both got the molecular formula C5H10. As I've said, A decolorizes bromine water, so it has to have a carbon-carbon double bond. B does not, so it doesn't have a carbon-carbon double bond, and therefore to meet that molecular formula of C5H10, it has to be cyclical. Now, we can draw any alkene with the molecular formula C5H10. I went with the simplest one in my opinion, pent-1-ene, and then we can draw any cyclical structure as well. Again, I've gone with the simplest one, which is cyclopentane. Now, it hasn't specified in the question how it wants us to draw these structures. It just says draw one possible structure. So whether you want to do that in full displayed or a version of displayed or skeletal, I think for cyclical compounds, skeletal is a lot easier, but for all of the others, I've gone with a version of displayed formula. For C and D, again, we've been given the molecular formula C2H4O2. It tells us that both of them have an absorption in the infrared spectra at 1,700 centimeters to the -1, which is a C double bond O group, but only D has a broad absorption at 3,350 centimeters to the -1, and that's representative of an OH alcohol group. So I drew my C double bond O. We only have 2 carbons, so it has to be the functional group of an aldehyde rather than a ketone. And then on the other carbon, to give me the OH alcohol peak in D, I drew my OH, and then I popped my remaining hydrogens into place, and that's my structure for D. For C, I can't have an OH alcohol, but I have to have a second oxygen to meet the molecular formula. So as well as having the C double bond O, I've decided to put the second oxygen to make an ether, which is when we put the oxygen in between 2 carbons. You could, I think, have made it into a carboxylic acid and put the OH there. The reason why I was a little bit nervous of doing that is that we can identify the OH acid peak on an infrared spectrum, and it didn't make any reference to that in the question. So that's why I chose to go down this route. But I did also, when I was first doing this question, draw out ethanoic acid as a potential alternative structure. Compounds E and F, they're both esters, so we've already been given a bit more information because we know exactly which functional group we've got. Molecular formula for both is C5H10O2. Then the extra piece of information this time is about proton NMR spectra. So E only contains 2 singlets, so we've only got 2 environments, and the hydrogens need to be next to no others for them to be singlets. F consists of 2 quartets and 2 triplets. Quartets are made when the hydrogens in that environment are next to 3 others, triplets when those hydrogens are next to 2 others. So in order for us to get a quartet and a triplet next to each other, we need to have a CH2 next to a CH3. And based on how many carbons we've got, it became quite easy to see how this was going to fall out. So for the 2 singlets, we've got 1 hydrogen isolated on its own over here to the left of the C double bond O. The other 9 hydrogens to make up the 10 are all in the same environment on the very right hand side of the structure, because it only has 2 peaks, so we can only have 2 environments, and that's the only way that we can achieve that, with them also both being singlets. In F, as I've said, to get a quartet and a triplet, we need a CH2 next to a CH3. Now there's 2 quartets and 2 triplets, so we need a CH2 and a CH3 in both positions. And I always start with the functional group, so I started with my C double bondo, single bondo, and that left me with 4 carbons. So I could put 2 before the C double bondo, CH2, CH3, and then 2 on the right hand side of the structure after the single bondo to give me my second triplet and quartet peaks. For compounds G and H, again we're given the molecular formula as C3H6Cl2. G shows optical activity, meaning it has to have a chiral carbon, but H does not. So for H there needs to be some sort of symmetry so that we don't have that chiral carbon. So for H, popping the chlorines on the same middle carbon, although again, like I say, there are options. You could have popped them on the end carbon, that would have also have worked. But we needed to have not different things on the middle carbon, because otherwise that would have generated us a chiral carbon. So carbon on the left bonded to 3 of the same things, carbon in the middle bonded to them 2 chlorines, which are the same, and 2 methyls, which are the same, and again the carbon on the right bonded to 3 of the same hydrogens. So none of those carbons are chiral. Tongue twister I didn't even know about there. And then for G, to create my chiral carbon so that G will show optical activity, I thought about how can I make the middle carbon be bonded to 4 different things. Well, move one of the chlorines and replace it with a hydrogen for starters, and that gives me a H and a Cl, and then I have to put the Cl somewhere, and that means that the CH3 is then not going to be a CH3 on the left hand side, which again makes those 2 groups different. So the middle carbon here is my chiral one. And then finally, we've got compounds I and J with the molecular formula C6H12. Now, both of them have an absorption in the infrared spectra at 1650, which is a carbon-carbon double bond, and neither of them shows geometrical isomerism. The proton NMR spectrum of I consists of 1 singlet only. So we've got to get all 12 hydrogens in one environment, and obviously to be a singlet, those hydrogens can be next to no others. J, while still not showing geometrical isomerism, has to be made of a singlet, hydrogens next to no others, a triplet, the hydrogens are next to 2, and a quartet, where the hydrogens are next to 3. And again, you'll get used to seeing that pattern with NMR, where you have 2 hydrogens that are split into a triplet. Where you'll have hydrogens next to 2 split into a triplet, and then you'll have hydrogens that are next to 3 that are split into a quartet. So I feel like I was easier because there was only one way we could create one environment. So again, when we know we've got a carbon-carbon double bond, I always draw that first with my 4 bonds coming out of those 2 carbons. That left me with 4 carbons to draw and all 12 hydrogens. So the only way I could keep all of those environments was the same, was to pop a CH3 coming out of each position. Now this won't show geometrical isomerism because we've got the same group coming out of the left carbon of the double bond and the same group coming out of the right hand side of the carbon-carbon double bond. So no geometrical isomerism, all in the same environment, the hydrogens, and also on the adjacent carbon to each of them there's no hydrogens, so it will be a singlet. For J, we still needed it to not show geometrical isomerism, so we still needed to make sure that at least one of the carbons of the carbon-carbon double bond had the same thing attached to it. Now again, to be a singlet, we had to isolate some of the hydrogens, and in order to get a triplet and a quartet, I knew I needed to have that CH2, CH3 pattern, and once I'd drawn my C double bond C, with 4 carbons left, I needed to have a CH2, CH3 and a CH2, CH3 coming out of those positions. That left me with only 2 hydrogens. Now these hydrogens on the left are the singlets because again, they're on a carbon. The adjacent carbon has no H's on it. Then we've got the 2 H's of the CH2. They are next to 3 others, so they would be split into our quartet. And the 2 CH3s, they would be next to the 2 hydrogens in the CH2 and thus be split into triplets. Because we only needed there to be 3 different peaks, a singlet, a triplet and a quartet, we needed to have some sort of symmetry. So we've got a plane of symmetry here, which would kind of go where the x-axis would be, so straight through the horizontally through the carbon-carbon double bond, and that means that the 2 hydrogens on the left are in the same environment, the 2 CH2s are in the same environment, and the 2 CH3s, their hydrogens, are also in the same environment. So there's quite a lot going on with that last one compared to some others, but each structure that you draw you only get 1 mark for. So it's 10 marks for deducing those different structures, which is quite a lot to do, for the marks that you get. So we do need to be thinking carefully about time and how much time you're spending on questions like this, because I think it could be very easy to spend way longer than 10 minutes, maybe kind of 15 or 20 minutes, depending on how comfortable you feel. And it might be with some of them, it's not worth it. And you might be thinking, okay, I'm not really sure what to do here, move on. If every structure is worth a mark, you might have been able to get E but not F. Brilliant. Get E down, leave F. Then you're still going to get a mark for E, hopefully. But like I say, you're not using up time that you need to be spending on other questions in the paper. Hopefully, I've been able to show how I arrived at these different structures. But if anybody has any questions on what I've said or anything hasn't been clear, please let me know. You can leave a comment on the video, send me a DM, reach out on Instagram, Facebook, TikTok, or send me an email. I'm always happy to help with queries, and I know some of these are quite tricky, so I am more than happy to take questions. Hopefully it has been useful, and I thank you all very much for watching. Hope you have a really lovely day.